When we use numbers, we often write them down in decimal notation, that is, in base 10. But that's not the only base we can use. After all, computers use binary, that is, base 2. Binary data can be really hard to parse, though, so often we represent that in hexadecimal, base 16. And then there's the fact that the reason we have 24 hours in a day, but 60 minutes in an hour, is because the Egyptians used to use base 12, half of 24, but the Babylonians used to use base 60. Now, you might see all this and wonder, we have all these different bases, but all of them are integers. Why not use base 3 halves, base square root 2, base pi? Well, as it turns out, it's perfectly fine to use non-integer bases, but they do act a little bit strange. So today on Math and Tea, the show where we talk math and drink tea, we're going to talk about non-integer bases. Let's get to it. Before we begin talking about crazy things like base pi, let's revisit how standard integer bases work. In particular, let's talk about place value notation. In place value notation, the place or position of a digit affects the value of the corresponding number. Let's say I write down 3003. While there are 2 3's in this number, the 3 on the left represents 3 thousands, while the 3 on the right represents 3 ones. Same digit, different positions, different values. Also, because we will be studying lots of different bases, we will represent the base we are using with a subscript. Here, since we are considering this as being written in decimal, we use a subscript 10. Let's start by interpreting the number 153 in base 10. We'd normally say this aloud as 153, or if we're being a little bit careful, 105 tens and 3 ones. Now let's consider how we might express this mathematically. What is actually going on here? Well, this is 1 times 100 plus 5 times 10 plus 3 times 1. But it will be really helpful if we don't write out 100, 10, and 1 because those are kind of arbitrary numbers. What we really want are 10 squared, 10 to the 1, and 10 to the 0. This last form is going to be most important as it generalizes the easiest. Let's consider 1101 in base 10. By this we mean 1 times 10 to the 3, plus 1 times 10 to the 2, plus 0 times 10 to the 1, plus 1 times 10 to the 0. If I now change that around to say 1101 in base 2, I'm not actually changing that much. I'm taking all of the 10s in the previous expression and replacing them with 2. It's now 2 to the 3, and 2 to the 2, and 2 to the 1, and 2 to the 0. The same thing happens if I try and interpret 1101 in base 7. Now I replace all of those 2's with 7. So it's 7 to the 3, and 7 to the 2, and 7 to the 1, and 7 to the 0. And in general, if I look at 1101 in base b, I use b to the 3, b to the 2, b to the 1, and b to the 0. We can interpret digits after the decimal point in the same way, except we're now using negative exponents instead of positive exponents. So 3.05 in base b means 3 times b to the 0, plus 0 times b to the negative 1, plus 5 times b to the negative 2. If you think of base 10, this is why we have tenths and hundredths, because that is 10 to the minus 1 and 10 to the minus 2. Now let's return to this 1101 in base b. If we look at this, there doesn't seem to be a reason why we can't replace the integer b with a real number beta. So let's do that. Let's say 1101 in base beta is 1 times beta to the 3, plus 1 times beta to the 2, plus 0 times beta to the 1, plus 1 times beta to the 0. That's meaningful, right? By the way, we will often refer to a base beta expansion as just a beta expansion. Well, if we do this, then we run into our very first problem. We don't want to use just any beta. We want to use betas that are strictly larger than 1. In particular, this keeps larger places to the left and smaller places to the right. By the way, there are such things as negative beta expansions, but let's not worry about them here, they're complicated. The second problem that comes up is trying to understand which digits we should use. In base 10, the set of allowable digits is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In base 2, however, we only use 0 and 1, and in base 16, that's hexadecimal, we use 0 through 9, then A, B, C, D, E, F, where A, B, and C, and so on are the numbers 10, 11, and 12, and so on, but expressed as a single digit. Now these sets of digits follow two rules. The first rule is simply that all the digits are integers, and this is a rule that we'll want to keep. You can have non-integer digits, but that's a whole other massive rabbit hole to fall down. So let's just stick to integer digits. The second rule is that the set of digits is as small as it can be while allowing for any non-negative integer to be written in a unique way using those digits. Uniqueness here is a useful property because it leads to compact notation. This second rule, however, we're going to have to ditch. In base beta, if I write down 1, 0, then this is probably not going to be an integer. Instead, we need to look at something else to guide us. So here are our two rules modified. The first rule is the same as it was before. All the digits are integers. But the second one is going to say that the set of digits is as small as it can be while allowing for any non-negative real number to be written using those digits, not necessarily uniquely. And I should emphasize here that the lack of uniqueness is not unique to non-integer bases. Even in just regular base 10, we have examples like 1.0 repeating equals 0.9 repeating. Same number, two different expansions. In fact, every number with a terminating expansion also has a non-terminating expansion. Terminating, by the way, means it ends in an infinite number of zeros. So how many digits do we need for beta expansions to be able to express every non-negative real number? Let's assume that, like for base B expansions, we will use a consecutive set of integer digits, 0, 1, 2, all the way up to some capital B. Also, instead of trying to show that we can get all non-negative reals, we only need to worry about getting the real numbers between 0 and 1. Recall that in base 10, multiplication or division by 10 moves the decimal point around. 1.59 in base 10 multiplied by 10 is now 15.9 in base 10. Likewise, 1.59 divided by 10 becomes 0.159. The same is true when we are multiplying or dividing by beta and working with beta expansions. Multiplying by beta shifts the decimal point one spot to the right, whereas dividing by beta pushes it one spot to the left. If we can represent everything in 0, 1 as a beta expansion using the digits 0, 1 up to b, then by multiplying all these expansions by beta, we can represent everything in 0 to beta as a beta expansion using the digits 0, 1 up to b. Again, multiplication by beta only shifts where the decimal point is, not what the digits are. And then we can represent everything in 0 to beta squared by multiplying by beta squared, and everything in 0 to beta cubed by multiplying by beta cubed, and so on, eventually representing everything. In trying to write numbers from 0 to 1, we will focus on numbers we can write to the right of the decimal point. The smallest such number we can write is 0.00000, in other words, 0. The largest number we can write is 0.bbbbbb, and so on. This is b times beta to the minus 1, plus b times beta to the minus 2, plus b times beta to the minus 3, and so forth, which is a geometric series and can be written as b over beta minus 1. So 0.b repeating will be at least 1, provided b is at least beta minus 1. This is satisfied if we let b equal the floor of beta, the largest integer less than or equal to beta. So if we let b equal the floor of beta, we know that we can represent 0 as 0.0, and we also have 0.b, which is some number larger than 1. Is that enough? It turns out yes, and we won't go into the full details. Basically, because there is some overlap, because we're able to write down a number slightly larger than 1, we can represent everything from 0 to 1 using these digits. If instead there had been a gap, if we had only been able to write something slightly smaller than 1, as it turns out we'd have a bunch of gaps. There would be gaps all over the place. So now we know what betas we can use, and we know what digits we can use. But as it turns out that beta expansions get weirder still. There's another problem that comes up. Let's go with a very simple example, beta being the golden ratio, 1 plus square root 5 all over 2. This has the digit set 0, 1. Now, for this particular choice of beta, we can write 1, 0, 0, and that's beta squared, which if we calculate it out is 3 plus square root 5 over 2. But that's just 1 plus square root 5 over 2 plus 1. In other words, it's 1, 1 in base beta. The same number has two very different simple expansions. But it gets worse. It in fact has infinitely many. 100 is the same thing as 11, which is the same thing as 10.11, which is the same thing as 10.1011, which is the same thing as 10.101011, and so on. And a similar phenomenon holds for almost all numbers. How do we choose which of these infinitely many expansions is going to be the right one? Well, let's return to decimal expansions. 25.50 repeating is the same thing as 25.49 repeating. When presented with numbers with two different expansions, we typically choose the one on the left. This is shorter, for instance. It can be written as 25.5, and it is also the greedy expansion. The greedy expansion is the expansion where we seek to maximize the digits farther to the left. In the example above, we have a 2 in the tens place, and there's no other option, and then we have a 5 in the ones place, and there's no other option for that. But we could have either a 4 or a 5 in the tenths place. Since we're going for the greedy expansion, we opt for the 5, and this forces us to have a 0 everywhere else. A weird thing happens, however, when we look at the greedy expansion for beta expansions. We can think of the possible greedy decimal expansions as being all possible decimal expansions except for those that end on repeating 9. A similar rule will hold for every possible beta expansion. If, say, beta is the golden mean again, then the possible greedy beta expansions are all the beta expansions except those that end on repeating 1 zeros, that is 1 0, 1 0, 1 0, and so on, or those that ever contain 1 1. And that's it. Let's see this in action. Let's consider beta to be the golden mean again. Then here we have the list of numbers from 1 to 11, but written as their beta expansions. As we can see, we never end on this repeating 1 0, 1 0, and we can never have 1 1. This rears its head if we look at the numbers 6 and 7. 6 is 1010.0001. Now we'd think that going from 6 to 7 we just add a 1 in the ones place, but we can't do that because that means we would have a 1 1. So instead, 7 has this much stranger expansion of 10000.0001. Things get even weirder if we look at base pi. Here are the numbers from 1 to 10 all in base pi. Now if you stare at this closely, you'll notice that the digit 3 does appear, but it only appears once. This is because the numbers 3 and pi are actually really close together, so 3 rarely appears in a base pi expansion. I'll include the Mathematica code I used to compute all of these expansions in the description below. And there you have it, a brief introduction to non-integer bases. We've really only scratched the surface on these. There's a lot more still to study beyond just how you write a number down, like how do you add numbers? Yeah, it's not easy. Before I sign off for the day, let me mention a brief application of beta expansions. Remember how I said that most numbers have an infinite number of different beta expansions? That turns out to be a really useful fact and can be exploited to make analog to digital signal conversion run more efficiently. But that's all for today because I'm out of tea again. Bye.